Hello student, welcome to our fourth lesson. Under this we have half-life. We start with the definition. Now this one is defined as the time taken for half of the number of nuclei initially present in a radioactive sample to decay. Remember, we are emphasizing the word radioactive. We call these keywords because the decay will only occur if the material is radioactive. And now, the time it will be taken for the half of that to decay is what we call the half-life. So, the half-life of a radioactive element can be calculated using three methods. One, linear method, formula method, and graphical method. We start with the linear method. This one involves dividing the masses or the percentages or the fractions by 2 after each and every half-life. In general, if N0 is the initial mass and T half is the half-life, then we have that the first one or the initial present is N0. After the first half, we have N0 over 2. After the second half, you take N0 over 2 divided by 2, you get N0 over 4. Then the third one, you take this one, the one that is present, you divide by 2. You get N0 over 4, and the process continues. This is what we call the linear method. We have an example. The count rate of a radioactive idiom falls from 3,200 counts per minute to 200 counts per minute in 220 minutes. Determine the half-life of the radioactive isotope. We proceed as follows. We start by writing our original. It was 3,200. You divide by 2. You get 1600. Again, you divide by 2, you get to 800. Divided by 2, you get 400. And 400 divided by 2, you get 200. Now, after every time, this one is half-life. So it implies that in our first half-life, we got 16. Our second, we got 800. Our third, you get 400. And our fourth, we got 200. So in other words, the total number of half-lives is equals to 4. But the time taken is 220. So to get the number of half-lives, we say that 4 half-lives is equals to 220 minutes. What about a half-life? You divide it through by 4 to get 55 minutes. So the half-life of that is 55 minutes. Then we have decay formula. In this one, it can be proved experimentally that N is equals to N0 into bracket a half raised to capital T over T, where N is the remaining count rate, N0 is the original count rate, capital T is the total time of decay, and small t is half-life. We look at an example. A radioactive isotope has a half-life of 2.5 hours. How long will it take for 256 grams of the isotope to decay to 32 grams? We proceed as follows. We start with our formula, then we substitute the values. Then, because we want to get the capital T, we have to make sure that we are left on the unknown on one side. So we divide through by 256. 32 divided by 256 is 1 over 8. Remember the power, we want to make this so that now the bases are the same. So 1 over 8 is the same as 1 over 2 to power 3. And because the bases are the same, then the powers are also the same. We employ the idea or the principle of logarithm and indices, the laws of logarithms and indices, that if the bases are the same, then the powers are also the same. Therefore, 3 is equals to capital T over 2.5. And to get the value of T, you multiply through by 2.5 to get that T is equals to 7.5 hours. Then from there, we proceed to graphical method. In this one, we have to plot a decay curve. After plotting, then we can be able to go to where we have the half of the material, the half of the fraction, the half of the mass, and get the time from the graph. So the law of radioactivity decay states that the activity of a sample is proportional to the number of undecayed nuclei present in the sample. And therefore, the half-life of a radioactive element is time required for its 1/2 of the sample to decay. So we are emphasizing on this so that when you plot the graph, you can be able to get the half. Because if this is the original amount or the original count rate, then you need just to go to where we have the half of that. And then you draw a horizontal line. Then where your line touches the curve, you drop a perpendicular line and you read that value from the time axis. Read that value. That will be the half-life. Remember, you have to check what is here, then get half of that, draw the horizontal line until it touches your curve, then drop a perpendicular line and ensure that it touches the time axis so that you can get the time. So the second half-life, as you can see, you can get it from here. You get the second half-life, the third half-life as that. This is what we call the graphical method. Note that in this graph, although the decay is approaching 0, as you can see, the curve is approaching 0, it never touches this mark because it never goes to 0. It will keep on approaching, but it will not touch our x-axis on this side because it never goes to 0. Then from there, we have an example. We have a graph. In this graph, we are supposed to get the half-life. If you look at this graph, our original, when the time was 0, our original value was 120, the number of counts. So the half of 120 is 60. So you draw a horizontal line where it touches our curve, you drop a perpendicular line, and that will give you your T1. And that is T half-life. You can proceed to come to the second one. Because this is 60, you move to 30 again. You draw a horizontal line until it touches the curve, then you drop. You get your second half-life. You can get the T half-life by subtracting T2 minus T1 to get that it is 60 minus 30 to get 30 seconds. Or you can just read what is directly. From 60 here, you drop, you read what is here. That also will give you 30 seconds. Then we have example 2. The graph below shows the activity of radioactive sample against time. From the graph, determine the initial count rate at t is equals to 0. And for us to get the initial count rate, note that the graph was not touching our y-axis or the count rate axis. So you have to extrapolate and ensure that it touches. And by so doing, you will find that our count rate is 300 counts per minute. As you draw a line, you extrapolate your graph. Then part 2, you are supposed to calculate the half-life of the radioactive substance. Remember, if you extrapolate, it will be at 100. So the half of 300 will be 150. So you're supposed to drop a horizontal line there. Then you have a perpendicular line there. Whatever is cutting here is what we call now the half-life. And in our case here, if you are very keen, it will be 1.6 minutes. Then from there, we have decay law. Now in this decay, first of all, we need to know that radioactive process is spontaneous. It is random. In other words, you cannot predict which nuclei will undergo decay next because it is just a random process. You cannot pinpoint and say that this nuclide X will decay next. No. And then the disintegration is by choice, or it is governed by the chance. And this is because we are referring or we are working with a large number of atoms. So the choice of the nuclide that will decay is governed by chance. And therefore, the decay law states that the rate of disintegration at a given time is directly proportional to the number of nuclides present at that particular time. Note the keywords. The rate of disintegration is directly proportional to the number of nuclides present at that time. So it can be expressed mathematically that change in n over change in t is directly proportional to the negative capital N, where n is the number of nuclides present at that given time. It is negative because it is decreasing. This number is decreasing. So it implies that dn is equals, now we want to equate or to replace the sign of proportionality with an equal sign and a constant. So it will be dn over dt is equals to negative alpha n, where our constant is called decay constant. This one, lambda, it is the Greek letter lambda, is called decay constant. And the negative sign, as I have mentioned earlier, shows that this number is decreasing as time increases. dn over dt, this part is what we call the activity of the sample. And activity can be defined as the radioactive element, or activity of a sample of a radioactive element is the rate at which its constituent nuclei decay or disintegrate. It is the rate at which the nuclei is decaying. Now, this activity is measured in disintegration per second, or what we call Culia, that is CI units. And one CI is equivalent to 3.7 times 10 to the power 10 disintegration per second. So in other words, as you can see, this part that we are calling activity is measured using disintegration per second. So 1 microculia is equivalent to 3.7 times 10 to the power 4 disintegration per second. Then from there we have the assignment. Again, the assignment is just testing what you have just learned. So make sure that you're able to revise and attempt the assignment with a lot of confidence, ensuring that you're going to get everything. So thank you, and let us meet in our next lesson.